Go. James e Mariana, please. Okay, good afternoon, everyone. Just start the important meeting that was hosted by National Center of Energy and Materials and the Max Planck Society. First, I would like to thank you, Mariana and James, the organizer of this meeting, and welcome everyone. The people that doesn't know the synchrotron, tomorrow, 5 p.m. is exactly? Yeah. You can't say more detail, okay. You have a visit, and then you have to start. Please, Mariana, you have a few words.
Yes, I just want to say a few words before we start. It's a pleasure to be here. This is a meeting that is partially financed also by the Max Planck Society. This is money related to a tandem group I had with Luana Pedrosa, who is here sitting at the audience. And there is, we could partially organize a meeting here on the topic. So we'll have a session just about water and properties of water. That's the subject of her group, and it's really a pleasure to be able to bring some people from the Max Planck, some people from Germany here, and to be here again. Muito obrigada por todo mundo que está aqui. É muito legal estar aqui hoje e eu espero que todo mundo tenha entendido inglês também. A gente vai falar inglês agora, mas obrigada em português também para todo mundo que está aqui. É muito bom estar aqui de novo.
Well, thank you all for coming. It's good to see this auditorium full of people. So I will just give some things that you have to know about this conference. So the first thing is we have a restaurant here that you can go, but after 1 p.m., okay, 1300 hours. But we also have some food trucks that you can go earlier. So usually the sessions here, they will end around 12, probably a bit later. But the restaurant for visitors opens only after 1 p.m. But the food trucks are available. So we'll have a conference photo just after Mariana's talk in the first coffee break. So it's a longer coffee break for us to have this conference photo. Everyone is here. Let's take advantage of that. So also we will have a cocktail tonight, okay? It's free. You can stay here from 5 to 8 p.m. We'll have some beers, some food, so feel free to stay over. Tomorrow we'll have a conference dinner at a barbecue place. Later we'll send you the address, but there each one has to pay for their own dinner, okay? So it's not funded by us. And also we'll have a visit to Sirius tomorrow, 5 p.m. And I uploaded a form on the website. So please go to the conference website, and in the agenda tab, there is the form there with a red button. It's just yes or no if you go or not. So we'll need to know more or less how many people will go to this visit. So please fill it. Okay, so the conference program is at the website. It's already updated. There were some problems with the talk's time, but now it's all updated and you can check it there. Okay? Fazio? Não tá. So I think that's it, and we can start opening the session with Mariana.
Before Mariana started, only to say that Mariana was a student of our director. Yeah, it's not too long time ago. That's just here in São Paulo University. And then the first talk you give by Mariana, Rossi, on revealing nuclear motion at the nanoscale. Okay. You change. Okay, sorry.
That's completely fine. Is it okay with the microphone? It's better, right? If I talk in the microphone. Super, yeah. So I'll feel like, some giving a gig. So yeah, so welcome here to the talk. The title is a little bit different, but the content is not so different. So today I will talk about the quantum properties of weakly bound systems, and I hope that you enjoy what I'll have to show. I want to start by actually not talking about science, but showing the group. So we are in Hamburg at the moment at the Max Planck for the Structure and Dynamics of Matter. It's a permanent independent group that we have there at the Max Planck, and we're called Simulations from Ab Initio Approaches. The acronym is SABIA, so everyone who is here understands this acronym, which is very different from anywhere else where I normally speak. And these are the people. They're actually all here today, as the Kun is coming later, and Alexandre was there last year as a sabbatical, so he did a sabbatical in the group, and so he was visiting the group, which was very great. It's funded, the group is funded mostly by the Max Planck Society, but also we have external funding from the European Union, Marie Curie Actions, the ERC grant that just started last month, and the German Research Foundation, which really helps us. And because I'm here today, and here's a special place to be, I just wanted to tell a tiny little bit about myself. So I think it's quite funny because I was born here. We are here today, right? And I was born here, okay, in the 80s. So it's the closest talk I've ever given to the place I was actually physically born. And yes, and then I did my undergrad at University of São Paulo and also my master's from 2001 to 2007. Fazio was my professor at the university, and I really thank him and many other professors they had because they are fundamental for the path to the present. And then I went to Berlin to do my PhD at the Fritz Haber Institute. I was there from 2007 to 2012. Then I moved in 2013 to the University of Oxford, and I did a postdoc there. Yeah, and these icons are about the weather, right? I had great weather in Brazil. It became really bad in Berlin. It's kind of bad in Oxford. And then after Oxford, I went to Lausanne, to EPFL. Actually, James was also there when I was at EPFL, so we were there together. Robert, who is here today giving a talk later, was also at EPFL when I was there. And that was the year of 2016. The weather was actually great there, I think. And then after that, I went back to Berlin to start my own group. That was a 3 years short group, a small group funding, and then 2020 I moved to Hamburg, where I am now. The weather is considerably bad there, considerably worse, even I think, than the other places, but it's a great place to be. And we are actually also at a synchrotron facility in Hamburg, so it's interesting. So it's called DESY. It's a very, very large light source close to the European X-FEL, which is the largest X-ray source in I think, yeah, one of the only ones in continental Europe. And we have the group there. That's where the Max Planck is, and this is the present. But there is also a little bit about the future. Next year, I'm moving to the University of Cambridge, so this is already done deal. This is me signing a very old book at the University of Cambridge, and I'll take up the Unilever Professorship for Molecular Sciences at the chemistry department there. And yes, so I mean, if very bright students want to come by, please come. Okay, and yes, so that's the announcement. Okay, now we go to science, if that's okay. So we start the real talk. So the talk today is about quantum properties of what I call weakly bound materials, and I wanted to motivate both why we really want to see a lot of quantum things and why we care about this, what I call weakly bound materials. So this is a very general slide that most of you here, I don't need to convince you that our world is quantum, even though we don't see it quantum when we look at places normally. This is, of course, ChatGPT type of way of seeing what the world is. So it has two suns, but other than that, it's quite normal. But sometimes, you know, like sometimes you don't need to look too small in order to see quantum at the macro scale, right? One very well-known experiment is the superconducting transition here, where you see the Meissner effect, right? So you have magnets, and then when it becomes superconductor, you have this levitating cube. And this is a manifestation of quantum mechanics that you can actually see in the macro scale, which is not very often that you can see that in the macro scale like that. But the truth is that without quantum mechanics, I couldn't be giving this talk. I couldn't have my computer. I couldn't have a laser pointer. It's all about quantum mechanics, everything we use today, right? And I'm not gonna, we don't do research on quantum mechanics at the macro scale like that, but actually at the nanoscale. So we look at the quantum mechanical properties of materials, specifically of materials that I call weakly bound. Materials that are weakly bound, they are predominantly stabilized by what we call weak interactions. Weak interactions are hydrogen bonds and van der Waals interactions, for example, and they can be of many different types. So I'm showing here a few different types of such materials. They can be molecular crystals, like drugs, like paracetamol, aspirin, and so on. They are molecular crystals. They can be molecular liquids, like water, very well-known molecular liquid, or van der Waals heterostructures, so these stacks of 2D materials that are predominantly bound by van der Waals interactions. And what is even maybe more interesting to us, the combination of these structures, so molecules together with 2D materials. And what is specifically interesting to me, to us in the group, about this kind of materials, is that because they are predominantly stabilized by these weak interactions, they undergo very wide range atomic motion. So the motion of the nuclei can be quite large. And there's a large electron vibrational, electron phonon coupling in this type of materials that essentially makes it impossible to understand their electronic properties without actually also describing the properties of the nuclei, how they move, and what they do to change the electronic properties of the materials as well. One such example is even very well known. It's work that we did a couple of years ago with experimentalists in Berlin, where they were looking at single crystal pentacene, so pentacene single crystals, and they were looking at what happened to nuclear motion by measuring femtosecond electron diffraction after they excite the electrons to the singlet state. So they are looking at the singlet to triplet transition in pentacene crystals. And this is their measurement. So what they see is that in some Bragg diffraction peaks, after you excite, which is, I have a pointer here, which is after they excite with the laser, they have some Bragg peaks that oscillate in a coherent fashion, and this oscillation has a characteristic frequency of 1 terahertz. And we, together with them, using theoretical modeling, we could tell them which motion that corresponds to, that was the motion. And then you see which type of nuclear motion accompanies really this singlet to triplet transition and what it does to this type of electronic transitions. So this is just to motivate that we need to care about nuclear motion. It's very important also for the electronic properties, specifically of these materials. And the question is, how do we describe nuclear motion in the computer, right? So the start is the usual start from quantum mechanics, is a Schrödinger equation that I write here on the top of my slide. So H here is my Hamiltonian, K is the kinetic energy, V is the potential, and this is the known time-dependent version of this Schrödinger equation, right? And everyone normally starts with the Born-Oppenheimer approximation. I'm preaching to the choir here. I'm sure everyone knows about this. It says the mass of the nuclei is much larger than the mass of the electrons, so the kinetic energy of the nuclei is much smaller than the kinetic energy of the electrons, and so you can consider a nuclei as fixed point particles. I'm saying it very fast, and then you can separate the wave function into multiplication, only one single term, right? That is the nuclear wave function times electronic wave function. And with that, you're able to write a Hamiltonian only for the electrons, right? So, and then you have a Schrödinger equation that is only for the electronic subsystem, in which the nuclei only appear as charged and fixed point particles, defining this external potential, essentially, where you solve this. And that's how most work is done. You stop there, nuclear fixed point particles, and that's it. But this is really something that, as I already told you in the beginning, cannot be sufficient depending on the material that you're looking at. Water, take a glass of water. If you had a magical magnifying glass and you would look at that glass of water really close by, you would see that molecules are all the time moving, right? And they are moving non-stop. And this movement also is related to then the electronic properties. If I take snapshots of each one of these configurations here, and I look at the electronic density of states, they are changing like this all the time, right? And what you see really as a property of the material is some type of average, depending on what exactly you're measuring of these types of differences. So how do we let our nuclei move? How do we go beyond them being just fixed point particles? You can say, okay, so if I can solve the electronic subsystem for fixed positions of my nuclei, they basically will define an external potential, so the solution for the electronic subsystem, where the ions can move, right? And so you substitute, so you take away the electronic subsystem, you don't have those explicit degrees of freedom anymore, you just have an effective potential depending on the position of the nuclei. And with that, you can define a nuclear Hamiltonian. This nuclear Hamiltonian will have a kinetic energy operator and a potential energy operator, which is now my Born-Oppenheimer potential, right? And then you can, for example, say, well, if nuclei are classical particles, I can remove the hat of the kinetic energy operator and just solve a classical equation of motion for the nuclei. This is one way to let the nuclei move in the computer simulations, right? But in this way, my nuclei are classical particles, and that's what you normally call molecular dynamics. So that is also something that can be insufficient, yeah? And this is the end of this introductory part of the talk. And the reason why it can be insufficient can be seen in many ways. I think this is a very pictorial way to see why it can be insufficient. For example, if you go to the thermodynamic properties, so the statistical thermodynamic properties of my system, and I calculate the expectation value of the kinetic energy for classical particles, I'm sure you have all learned that this is 3 It doesn't matter which system it is. That's the result of classical mechanics, okay? But if you go to quantum mechanics, that's not the result. And in fact, you cannot really have a closed form for the result for any system. You can only have a closed form if you have a system of harmonic oscillators, which is an approximation, but sometimes a good approximation to understand how things work. And if you do that for the quantum harmonic oscillator, you see that this is actually the expression that you get for the expectation value of the kinetic energy, and it has a dependence on the mass of the system, so it's different for different systems as well. And when you go to very high temperatures, which is the classical limit, for example, you go back to here, or very high mass, you also go back to the classical result. But because things are really not classical, if you would, you can see, for example, that this type of terms, they enter on the calculation of reaction constants, reaction rates. These terms are very important. They're the kinetic energy part of the Hamiltonian. And this is related to the calculation of the pH. Water's pH is 7.0. We all know that. That's how it is. It's good for us. Life depends on that, okay? And you can calculate, you can measure the pH of DOH, D2O, and T2O, so heavier isotopes of water. And if you plot them on this plot of 1 over the square root of mass of this hydrogen isotope, you have a line. And this line, if you extrapolate to infinite mass, which would be the classical limit, gives you a pH of classical water of approximately 8.5. Which is very, very different, and in fact would completely screw up all the the reaction equilibria we have in our bodies and so on. So we cannot live without quantum mechanics, right? Also at this level, not only at the electronic level. And so it is really important, I mean, yes, that we describe it like that. And you can also do that in the computer. This is something that my group does quite proficiently, and there will be other talks that will go deeper on this type of formalism, which is the Feynman quantum statistical mechanics based on Feynman path integrals, in which you can show that the thermodynamic properties, so the partition function of a quantum system, can be calculated by calculating the partition function of a classical system instead. And this classical system is a very special and well-defined system in which each quantum particle gets mapped to a ring polymer containing a certain number of beads, and only when these beads go to infinity, you get the quantum mechanical expectation value, so the quantum thermodynamics. This is a very good thing to put in the computer because you get rid of this exponential growth of trying to solve this operator for many body system. You now only have a classical system, and the classical system scales quite well with more bodies, right? And so this is very easy. You will see in many examples in the next slide to computationally resolve, but you need to take care with this limit here of p going to infinity. In practice, is a convergence parameter in which you just make many replicas of your system, so it gets mapped into this type of picture. Each atom in this system gets to be one ring polymer, so in the end you have several replicas of your system, and you just check how many of them you need until you converge your quantum property that you need. Yeah, so normally it's between 16 to 32 replicas if you have hydrogen atoms inside at room temperature, and it increases at lower temperatures. So that's a little bit of very condensed introduction on the type of tools that we use in order to simulate our systems. You'll see more of that, I think, in upcoming talks. And nothing of that would be possible if we didn't implement that into codes. So we also develop heavily electronic structure and nuclear motion codes. So for the electronic subsystem, we co-develop FHI AIMS. That's an all-electron numeric atom-centered orbital code that does density functional theory and beyond density functional theory. We did a lot on response properties of the density. We implemented many functionalities there. And I would like to highlight one, I think, very important achievement with the code, that we get density functional theory hybrid functionals, these functionals that have a fraction of exact exchange and can make the electronic structure much better for this type of molecular materials that I deal with. We can do them for more than 10,000 atoms, and this is not machine learning, it's just electronic structure. In this publication here, I think Christian Carbonha will tell more about that in his talk later. And then on the nuclear motion side, we are core developers also of the IPI code, which I help coordinate as well. And there we do this path integral molecular dynamics, in which you can grasp anharmonic quantum effects. And we have a new release of the code last year, which is version 3, in which we really did it a lot better to communicate with machine learning potentials on the back end, which is how the field is evolving. And with that, we also join it with statistical mechanics and machine learning in order to do some applications. So now I take the last half of the talk to show some applications of this type of motion. I start by talking about this electronic-driven anharmonic motion in charge density wave materials. So this is a case where I have a 2D material that's tantalum disulfide, and tantalum disulfide is a metallic 2D material, right? And as a metallic 2D material, when you cool it below a certain temperature, it forms what you call a charge density wave state. It has a phase transition onto this structure, which is displaced from the fully symmetric points in the lattice that is characteristic of this charge density wave. And this is how it looks. And charge density waves are interesting to be studied because they are related to the superconducting transition. This material also becomes superconducting at a certain temperature, and it competes with superconductivity. So you want to understand how to maybe suppress this phase in order to enhance superconductivity. And here we teamed up with a group in the University of Hamburg, the group of Tim Welling, which does interesting models for the electronic structure of these materials. These are called downfolded models. These downfolded models, they are a type of very fancy tight binding model for this type of systems, in which they can also include nuclear motion inside this parameterized Hamiltonian that they end up here, in which they only treat explicitly some low energy bands and integrate out all the high energy bands. The interesting thing here is that you start from something like density functional theory, you just get a model which is ab initio parametrized model, and then it's much cheaper than density functional theory, so you can go to very large system sizes, but you still have electronic structure information from that point of view. And it works very well. You can see here what was the DFT answer for this displacement along the charge density wave transition and what this model gives in there on top. So we use this model. And we use this model to do something quite fancy. We use this model to really observe this phase transition in these materials. So we take large flakes of these materials and we do what we call path integral replica exchange molecular dynamics. That's an enhanced sampling technique in order to look at really phase transitions efficiently so that you can sample the whole thermodynamical space nicely. You have several replicas of your system distributed from low temperatures to high temperatures. And the path integral way is that in each replica you have the system represented as many replicas of this ring polymer. So you get the quantum statistical mechanics behavior of this whole phase transition. So you have to simulate that for about 500 picoseconds, all replicas that you have, and then you can look at transition fingerprints from statistical mechanics, right? You look at the heat capacity or structure factors and so on, and see if they change continuously, and that's how you get the phase transition. This from our simulations. So here you see the heat capacity, and you see that at a certain temperature here you have a peak. This peak depends on the size of the system. So you have finite size effects, which you can bridge by going to very large system sizes. And you see that this discontinuity here is a phase transition. You want to know what it is. It is our phase transition, but we can look at other fingerprints of that. For example, the structure factor. This is a structure factor in Q space. When you have the charge density waves, the Brillouin zone of the material becomes much smaller than if it's completely symmetric. And this is the gamma point of the mini Brillouin zone, essentially, that you have at the charge density wave transition. And as you heat it up, you can look at, this is from our simulations, you can see that at 200 K, that fingerprint is gone. The charge density wave has melted. And the transition happened somewhere here, which is consistent with the heat capacity peak. You can then record the intensity of this peak as you increase the temperature, and you see here this inflection point of this curve to be the place that we nail the phase transition to be. I'm first showing here simulations that we did with classical nuclei, so not considering that my nuclei are quantum mechanical particles. And then we can redo the simulations looking at quantum mechanical effects. So that's this other curve here. And you see that essentially the charge density wave melts faster with quantum mechanics. That's a consequence of zero-point energy, zero-point motion of the material. And you have a shift of about 20 up to 30 K of the phase transition there. And you can see that that's mainly a competition between diffuse scattering and Bragg scattering that happens there. You can understand a lot about which modes are related to this phase transition. I urge you to read the paper a little bit more for a deeper analysis there. Yes? So this here is just, so what I'm showing here that I didn't have time to say is is actually the difference of the, so it's the ratio of the structure factors if I calculate them with classical nuclei and quantum nuclei. So if they are 1, they are exactly the same. And if they're above 1, there is more classical than quantum, and if they're below 1, there's more quantum than classical. So what you see here is that at 81K and 96K, you have red peaks here, which means that classically the charge density wave is still there, but quantum mechanically it's not anymore. That's it. So, yes. So then all of this was done with these downfolded models, which are very nice, by having this, and they are still very nice, right? Because you have this tight binding type of idea, so you can really understand easily what type of electronic states give rise to certain enharmonic coupling between your atoms. There's a lot of understanding you can gain from that. But they are also limited in some ways because they are not transferable. It's very difficult to parameterize each one of them, and you need a lot of previous know-how in order to use each one of them nicely. So in order to treat the electronic structure maybe in a more universal way, all-encompassing way that is still much cheaper than density functional theory and allows us to do very large system sizes and main materials, machine learning is really the answer nowadays, as it shouldn't be a surprise to many. So in my group, we have been developing for the past 5 years or so now a method to learn the electronic density. So the whole 3D spatial distribution of the electronic density itself. It's called SALTED. It's symmetry adapted learning of three-dimensional electron densities. These two guys were the ones really starting that. Alan was a postdoc in my group. He's now a professor at York University. And Andrea was in Michele Ceriotti's group. We did it together to start. And he's now a permanent researcher in Paris. The way that this procedure goes, I will not go into the mathematical details of the procedure, is that you get your electronic density from DFT, from density functional theory. Then you do a procedure that is called density fitting or resolution of the identity. So you re-expand your density into a linear combination of some new numeric atomic orbitals or Gaussian atomic orbitals that are specific for this type of expansions. Then you pose a symmetry adapted representation for the coefficients of this expansion, of this density fitting expansion. The symmetry adapted part means that the coefficients, they multiply some atomic orbitals that have a certain YLM, a spherical harmonic related to them, right? And each spherical harmonic has an angular momentum that tells how it transforms under rotations. So each coefficient will be related to a certain spherical harmonic that has a certain rule to transform under rotations. And what we do is that we train a Gaussian process regression model that knows about the angular momentum dependence of each one of these coefficients. That's what it means to be symmetry adapted. So then we train this, it's a Gaussian process regression model, it's not a neural network in this case. And these models are interesting because they are quite data efficient, so you don't need many points to get a very accurate model. But they are limited as well in terms of the size they can go to. If you have a very large data set, you really need a neural network. You cannot go with these methods for reasons that will become clear in the tutorials that we'll give to the students in the second half of this thing. And then with that, we can predict the density or the density response, as you see, and we did a method that works for many material classes. It works for isolated systems, periodic systems. It can be a liquid, a solid, a metal, a semiconductor. It doesn't care. It really works for everything, but it's not yet universal. It's not a single model for everything, okay? So, and then we can, if we predict the density, then once it's trained, so I can give a new atomic position to my model, and then it will just predict the atomic density. I can reconstruct it into the code, and I get all types of properties from this electronic density. So we did many experiments with this method. One that tells you how good it goes into the electronic structure is that by predicting the density of liquid water, we can then calculate the energy gap of different snapshots of liquid water, something I had in the beginning of the talk. And these are the reference gaps, these are the predicted gaps. They're not perfect, but note that this model is not targeting the energy gap. It's targeting only the electronic density, right? So I'm just getting this as a derived property out of the electronic density, and I can tell you it can get much better with more data. You can see that it also gets very well the spatial distribution of the HOMO and the LUMO orbital, right? So this is the one that comes from density functional theory. This is the one that the ML model predicts, and this is the LUMO. You can barely tell the difference. This doesn't work only for this type of materials. It works for big 2D twisted bilayer systems. So this is graphene, twisted bilayer graphene. We trained a model in which we had only small structures of bilayer graphene that were not twisted. So this is only 2x2 structures or so that we trained the model on. Yeah, and we displace them with respect to each other. We jiggle them around. That's how we build our training set here. And then after training, we try to only predict. This is the only prediction on a bigger twisted bilayer structure. This is 3.15 twisting angle. The magic angle is 1.1. It's much bigger than this. But here we can still do the DFT calculation. And this is the band structure of this twisted bilayer structure as I predict from my model or from DFT. So the model can really extrapolate over system sizes very well. So you need data from very small systems, and you can predict to large systems, and you can get these fancy properties. That's not all, but I'm coming to the end. You can go beyond the density, and you can see the density responses as well. This is a little bit more challenging because the density response is not anymore a scalar field over space, but it's a vector field over space. And predicting vector field is something that in machine learning is not so common. And so it's interesting to look at that also because the response of the electronic density to perturbations gives you a lot of information like electron vibrational coupling, dielectric properties, or vibration spectroscopy cross-sections, right? And what we tried to do at first is to predict the electronic density response to electric fields. So how the electronic density responds to a homogeneous electric field that is applied on it. And one important thing that we need to take care there is that the model should be equivariant. What does it mean to get an equivariant machine learning model? Is that if I have my model, this function that I want to predict, and I rotate my input, so this D matrix, a rotation of X, which is my input, then I should get the rotated prediction in the right way. Okay, that's how it is. For the vector field, it means that if I have a water molecule, this is my vector field, and then if I rotate the water molecule, it rotates together with the water molecule. That's what it means. And this should be embedded into your machine learning model. So we had a model to predict this type of electronic density response that was from 2023, and it was not fully equivariant. So if we had several different just rotated structures of the same water monomer, they are just rigidly rotated, and we tried to predict the electronic density response of these. This is the errors that we were getting. They are very small. They are like 1% in the root mean square error, but they are different for the structures that are just rotated with respect to each other. And they should be just the same because it's the same prediction, right? So we redid an equivariant model this year. And now you see that the errors are much smaller, but more importantly, they are all the same, okay? And this scales to many other structures. So the new model is really the average error over many other conformers is much lower than what we had before, and it is really equivariant. And that allows us to do many fancy things as well now. So we want to, look at more catalysis-like or reactions on metallic surfaces or metallic nanoparticles in this case in the future. And what we can do there is that we can predict the electronic density response of these metallic nanoparticles, from which we can calculate the polarizability of them. That's what I plot here. And we can train on small clusters as well and extrapolate to bigger ones. This is the largest one we did. And I just want to call attention for those working in the field that in this case, we really see the necessity of including long-range interactions in these descriptors that we have in the machine learning model, because the density response of a metallic system is a very non-local property. It happens at the surface of these particles. And so only if you have these long-range interactions, you can get this very well-known scaling law for spherical nanoparticles of the polarizability that scales with the volume. And I will end my talk here in the interest of time. So there was one more very interesting thing about machine learning for driven atomic motion. It's work from Elias Tocco, who is my PhD student here, but I will not go into that because otherwise my talk will be too long. I will instead just go to the end of the talk. 1 second. and this is just the slide to end the talk. So it's really interesting nowadays that, I mean, I have not talked about the machine learning force fields, that was this last point, but you can predict the electronic structure, you can also predict the forces on the nuclei, so you can move your atoms as well, because of, using the electronic structure that you have predicted. And you can even drive this nuclear motion based on this electronic structure, which really joins everything together with my motivation in the beginning. And we can really reach first principle accuracy on these systems of many, many thousands of atoms now, using machine learning, using very high level electronic structure data that we put in the model. And of course, more puzzles related to the quantum nature of atoms can be solved. And in the future for us, we plan to look more at charge transport driven reactions in confined architectures and universal machine learning models for this electronic structure, which Microsoft has started working on, so probably we'll lose the fight, but I mean, it's okay. If the tool is out there, it's good. And then, yes, going to atomistic simulations for non-equilibrium, non-adiabatic nuclear motion, which you might hear a little bit more later on today. Thank you very much for your attention.
Thank you very much, Mariana. Lots of work. Very nice talk. It's open for questions, comments, please. You identify and say your name. Yes, you need.
Thanks for the talk, Mariana. I have just one question regarding, I think it's slide 21 or 22, about the possibility of predicting the charge density of a quantum system via your machine learning model.
Yes.
My question is, can we go beyond and not only predict the charge density, but each quantum state on each K point and each band index? Thank you.
Yeah, so the way we did this model, which I could maybe pull up, 1 second. Yes, no. So the way we did this model is really targeting the electronic density. There are other models, like you might have heard about Deep Age and so on. They target directly the Hamiltonian. And then if you learn the Hamiltonian, it's also something derived, right? I mean, from the Hamiltonian, you can then derive the electronic orbitals. We can also get that here, right, from the density. We can get the orbitals. I think I showed the orbitals of water, right? So we are getting that out of our electronic density. But it's an indirect prediction, just like a Deep Age is an indirect prediction. I think targeting directly the orbitals, you can do it. I mean, why not? You can machine learning anything you like. But it might be difficult unless you have a very specific orbital in mind, because it's a quantity that is very non-local, banking on not having to guess the symmetries of the Hamiltonian and just, getting just that right and then deriving it from that seems to be a better solution so far. Yeah.
Gabriel.
My name is Gabriel. I will present next. So the previous question, the next speaker will talk a little about this, but I have a question on this slide. So you are predicting the charge density. Are you using single shot in this density, or are you doing SCF afterwards to get the predictions?
No, it's a single shot.
Single shot.
Yeah.
So it's good enough. And just a quick question on your data set of polarization properties. How large is your data set? You changed the electric field response properties?
Yes, it's about, you can see it here maybe on the slide I didn't have. So this is the old method that was not equivariant, that's why it flattens out, but it's always about 100 structures, no more. It's between 80 and 100. These GPR methods are very data efficient. They're nothing compared to neural networks, but they are non-parametric. So the more data you have, the larger the kernels are, and quickly the kernels don't fit your computer anymore. So, yeah.
Okay. Rodrigo.
Thank you, Mariana. Very nice talk. I have a simple question about the CDW problem that the first one you discussed.
Yeah.
How do you determine the transition temperature in each case from your plot on?
Right. So 1 second. So yeah. So what we actually calculated was the heat capacity. Yeah. So we look at the transition temperature by the peak on the heat capacity.
And you have another plot on.
Yes,
okay.
exactly. So we looked at the heat capacity, we saw phase transition. But I mean, the heat capacity doesn't tell you what is this phase transition. So you need another order parameter to kind of see which it is. We chose the structure factor. And then we fit a curve here and we look at the inflection point.
And do you have any finite size effect? Do you do any finite size scaling?
We do. So you can see it there. So you can see that these are different unit cell sizes, 15 by 15, 17 by 17, 18 by 18, and 21 by 21. And you can see that the peaks in 15 and 17 and 21 are a bit shifted, so that's the finite size effect that we see there. But you see another very interesting thing, that in the 17 by 17, it's not there. Yeah? And the reason why it's not there is very interesting because it's very deep. So this is a 3 by 3 charge density wave. And it couples to a phonal mode that is commensurate with a 3 by 3 unit cell. And so if you have multiples of a 3 by 3 unit cell, you capture, and if not, no. Yeah.
Okay. Professor Gustavo.
Thank you, Mariana. Very nice results, and congratulations for the position. You make us all proud, you know. So, Mariana, here, for these charge density waves, do you see some structural symmetry breaking, or it's just charge? So, do you see some...
the structure changes. So, I mean, there's an instability on the electronic structure subspace that leads to a distortion of the lattice, like this. So the lattice, this is the symmetric lattice, and then when you have the charge density waves, it's distorted. That's why you see the peak in the structure factor. That's why you see these peaks here, because when you distort the lattice, you decrease the Brillouin zone, right? You know, so. The total energies, yeah, so this is more or less the energy range here. So it's the minimum, this is the charge density wave minimum, it's about 20 milliV below the symmetric structure. Yeah.
Gabriel.
Per unit cell. This is per unit cell. Yeah.
Hello, I would like to thank you for the presentation. And I would like to ask about the density response for external fields. And I would like to ask that even in ab initio calculations, we used to use corrections, for example, the dipole moment corrections to calculate work functions. And this methodology can turn this able to, with machine learning potentials to apply corrections, this kind of correction.
Yeah, so like the data that you generate in order to create these models, it has to be very clean data. So you should, apply these dipole corrections and everything, But once you have the model trained and you're just predicting the electronic density, then there's no more need for that because the prediction already knows that that's how the data was generated, right? So it doesn't care about that. I mean, I take your question as an opportunity to say just one thing. It is, of course, possible, and that's the last part of the talk, to from these densities or whatever train a model for the dipole, right? I mean, so you can actually get the dipole out of this density, and then you can, really get properties of driven motion and driven field by coupling your system from this dipole that you predict with an electric field. And then you can do a lot of cool stuff that I didn't show about. This is a lot of stuff that Elia did. But you can look at the electric function of water like that. You can look at how water does electrofreezing. So you apply an electric field and it freezes. Yeah, so that's what is shown here. And this is all of this machine learning that is now targeting this dipole, for example. So, yeah.
Thank you.
Hey, Pedro.
Hi, Mariana. Thank you for your talk. You point that the electronic models are not universal yet.
Yeah.
And I would like to ask you that, in your opinion, what is missing? It is missing architecture, it is missing better and more data.
Yeah, I think something. So it's really, last week, Microsoft came out with a universal model for wave functions trained on diffusion Monte Carlo. And the data set they have is madness, okay? So they have a data set of the size, yeah. So data is a thing, because it needs to be a neural network, right? Because in order to go universal, we have learned recently that it needs to be a neural network. And the neural network is very large, and the data that they have is very large. And this thing about informing the model about some symmetries of the problem is very important. And the symmetries of the problem also change a little bit depending if you're working like they were working with wave function diffusion Monte Carlo, or we might work with electronic density. That changes. And figuring those symmetries out seems to be the key to make these things work. That's that. In data. In data.
Okay.
And when you comment that you implemented the Euclidean equivariance, what group of equivariance have you implemented?
SO3.
And thank you. SO3?
3, yeah.
Okay, thank you.
Any question, comments? Oh, if there is no question and comments, let's thank you again, Mariana. Thank you very much.
So now the session is over. So we go to the coffee break and conference photo, okay? So we come back at 15:40. Thank you all. Let's enjoy the coffee break. Just a quick note before. We have a change in our program for tomorrow because Professor Maurice de Koning is a bit sick, so he asked to postpone his talk to Wednesday. So Wednesday, Maurice de Koning will be talking at 11:20. So with that, there will be no, his talk was 10:40 tomorrow, and maybe Christian Carbonio can get his talk before. Christian is here? Okay. Can you talk a bit before tomorrow? Okay, great. So we'll have an even larger lunch break tomorrow. Okay. So now I will be chairing this session. I will just tell our guy there to change the slides in Portuguese, sorry. Ilum, pode colocar o slide do computador. So now Gabriel Schroeder will be talking to us. So Gabriel has his PhD in nanoscience and advanced materials at Federal University of ABC, with our esteemed Professor Fazio as a supervisor. And then he went to Harvard to make a postdoc with Caxiras. And now he's a researcher here at the National Laboratory of Nanosciences. So, Gabriel, the floor is yours.
Should be working. So, before we begin, I want to thank the organizers for this event, and I also thank Mariana for the previous talk, great talk, and it will introduce many of the things that are the scope of this meeting here, both electronic structure and materials informatics in general. So we'll be discussing these three days, and then the INCT meeting also. And I don't have a slide like Mariana about my background, but James said I come from Federal University of ABC here. So the pointer is quite weak. And now I realize that we are here in a very large family. So I can see, I was supervised by Professor Fazio here, as many people here also. So James here is my brother, Gustavo is my brother, Leandro is my brother. Luana is in the family, but not my sister. So we have a large family here, and many people are related. And it's quite a pleasure to talk to us. So I feel like home, and we are in family. You too, yeah. So this is like the hockey. We are in the same family. And the introduction by Mariana, thank you, great talk. And she already put some points on about what we are going to discuss now. So in universal interatomic potentials, we'll see what this is about. And nowadays, we are reaching the electronic structure, how these ideas and techniques are getting into electronic structure. And in our vision here, as a national lab, we use these things as tools to accelerate material simulations. So we are partly developing, but mostly trying to use these things to understand materials at the fundamental scales. So the broad general, when I talk about this for more general audiences, which is not the case here, is if we have a chat GPT for materials, but in the context of simulations. So not language models, but for simulations. And I don't think I need to introduce this, but AI is reaching nowadays into most areas. So not only physics, language, everything nowadays. And I was talking with Teldo. He invited me to go to Federal do Mato Grosso on the day that the Nobel Prize was announced. So I changed my talk, and we discussed about the Nobel Prize, why these things are being incorporated into everything in our lives. So this was in the press, many different things, and how these types of tools can now be used in any area, not only in language and so on, images, but also in physics, if you include the correct inductive biases. And I was tasked with being the first presentation on the institution, so I just want to show a little bit about what we do, what is the science we do in the context of a national lab here. So we are in CNPEM, which is the Brazilian Center for Research in Energy and Materials, which is a large campus encompassing the synchrotron light source. But also we have many national labs here. So we have biorenewables, biosciences, synchrotron light source, of course, the main one. We have engineering instrumentation, and I work at the nanotechnology lab. But we also have, most recently, Fazio is already pointing, we have Ilum, School of Science, which is a bachelor's course for undergraduate students. And we will have biosafety level 4, maximum security lab on the next years to come. This will be the first one in the world that is connected to a synchrotron light source. And the mission of a national lab, sorry, this is in Portuguese, is to bridge research being done in universities and academia with industry and applied technologies. And we try to do these things, to connect these things from basic to applied sciences and to get science to reach as far as possible. And here in CNPEM, we act what is called 4 axes of operations. So the first one is open facilities. So we are open facilities for everyone, not only in Brazil, but worldwide. And we have Axis 2, which is P&D, in-house research. We have Axis 3, which is innovation, trying to merge these things. And finally, Axis 4, which is training, education, and so on. And how we choose which areas to tackle. So we divide in 2 areas. One are the fundamental techniques. So we have what is called transversal competencies, which is particles, accelerators, bioimages, and so on. But we work here in theory and data science. And these things, all the techniques and facilities, they are applied in strategic areas, which are mostly in health, renewables, and sustainable materials. And these are the programs that we put our projects and research into. So we have R&D in renewable energy, sustainability, health, quantum technologies, and on the other hand, the enabling technologies, and we are here in computer simulations and AI. And this is just a quick overview of what we do. We try to merge these 2 things on the left side in our group. We use theory in computational simulations. These are the techniques which we are here discussing, DFT, Hamiltonians, molecular dynamics, and so on. And on the right side, we have data science, artificial intelligence. So what I'm going to talk about in results today, it's in this area where we are trying to do large-scale simulations or accelerating simulations using these types of tools, machine learning and deep neural nets, for doing simulations larger, more efficiently, or more accurate. And the people who are doing the research, they are here. So many people are here, mostly on the back there. So I thank for these people. And I'm going to talk about this, but we have a presentation by Bruno, who was also a student of Professor Fazio in the past. He will be talking on Wednesday about our efforts in this area, how to connect these tools, machine learning and deep neural networks, mostly for processing experimental data in different modalities. So images, language models, and so on. And these are just some highlights, just to show what are the recent things that we are doing. Always trying to incorporate experimental results, which we have many labs here. So this is type of things that we try to reach research into reality. And just, so this is a very general talk. This is the first day. I want to thank everyone. Just start slowly and then we'll get into the topics. So we, some years ago, 2019, we did a review on these things. So how things were evolving from the FT electronic structure. And at that time, the first few works incorporating machine learning and these ideas. And most of the works, they were trying to predict properties. And this was what we had available, data sets and so on. But nowadays, so 5 and some years after that, we have evolved so much. But the fundamentals and the history about how these things were, we reached these states are discussed here. So especially for students, I recommend this one. No pictures. No pictures on the QR code. Okay, it's fine. It's fine. So the discussion is very general. many people here already seen this discussion, is about how science evolves, and we can have two different views. This is a famous article by Freeman Dyson. That is, the science can be evolved by new concepts or by new tools. And then we have this famous sentence that when you have a concept-driven science, you can explain old things in new ways, but when you have a tool-driven science, you can discover new things that have to be explained. And we put AI and machine learning in this context, that we have a novel tool now that is in our toolkit, and we will apply it when it makes sense, but we will not apply it to everything as you would do with a hammer or with any other tool. So when it makes sense, we use it. When it doesn't, we don't. And then there's a different view that how science evolves now over time, but over large time scales. So we here have centuries, approximate centuries. So the first paradigm is called empirical science. So everything comes from real life and experiments. Over time, people started to condense the information that is contained in everything here and started to make very compact formulations about this science and formulate theory. So now you can explain novel concepts and generalize beyond what you can see in very specific experiments. The third one, and we see here in the time scales now reaching more modern era, is that computational science. Now you can not only have simple symbolic laws, but you can apply in different situations. So now we are talking about what we do, density functional theory, molecular dynamics, and so on. But what is called the fourth paradigm of science is data-driven science, where you now get all the information from all these previous ones, and you can try to learn new knowledge information from all this gathered information using AI, statistical learning, and so on. Some people claim that you can have a fifth paradigm where machines not only learn, but they now generate new knowledge. But you can incorporate this or not, but this is open discussion. And the most important thing is that knowledge, you can only gain knowledge. It's a cumulative function. So all of them work together to build new knowledge. All right, so what is the context about the science that I'm going to discuss here? So this, once more, this was introduced in the previous talk. We are talking about universal machine learning interatomic potentials, and what are the challenges and what we can do when we want to use them and when we cannot use them. So this started, we wanted to simulate different systems, and we saw these things, and it seemed great. We tried to use them, and it was not that great. So it came out as a paper about performance assessment and failures and how you can improve or where we can go. So this article I checked, it was published August last year. So this is less than a year ago. And when I presented this for not the first time, but a few months after the paper publication, this paper was already outdated. And every month that we see these results, it gets older and older. And this is less than a year old, and it's not current anymore. So it's quite impressive how we do science in this nowadays and what it means to actually publish a paper. And when the paper is out, maybe it's not already up to date. So this was the question. We have a new problem that we want to study, and we want to simulate a system. And the question is which machine learning interatomic potential we can use or we cannot use. And the idea is to compare these foundation models, universal ones. So the idea is that they can be pre-trained and then you just use it. But if this doesn't work, what we can do, we can either fine-tune it or train it more on your specific problem, or you train a specialized model that is not universal, but should work quite well for your specific problem. So just a comment, Pedro, who is also here, he works on this problem, and we are improving and moving forward on this, together with Mauri also. So if you have questions, you can ask Pedro later. And how this story all began. So we had in 2022, we published this paper, Stability and Rupture of Ultra-Thin Ionic Wire, here in LNano, together with our colleagues from microscopy and the theory team. So Fazio is also here, Rodrigo Capaz, Edson, who is coordinating microscopy facilities. And this was for the first time that it was seen the rupture of an ionic wire down at the atomic limit of an ionic system. So why this different from what is expected? Because ionic systems, they are quite fragile, especially in the atomic limit. But when we see the images, we see that they form quite ductile bonds. So they are very soft, and they form wires, and this is quite different, and then they break. So we wanted to understand why, in the atomic scale, you can form atomic wires, and why this is different from the bulk material that is quite fragile. And then this is seen quite nice work from microscopy. You can get really rich structural information so that we could, in principle, simulate these systems very closely to what is happening in reality. And just to have a sense of what this looks like, this is, I think, 2 times faster. So this is the final stages of forming these things. So we have 2 nanocrystals here. And then if you have some tension between them, just from the electron beam, from the microscope, they get a tension locally, and then you start to form these dynamics, and then they naturally or spontaneously form these things down at the atomic level at some point. So they start to thin out, and then you have some bonds and they break at some point. And we wanted the first question is why this happened at the atomic scale. And then this is now, last year, we have a larger scale problem before we reach this nanobridge formation, which is also interesting, but we couldn't understand at that time with simulations at this spatial scales. So I don't think we need to introduce much why we want to use machine learning interatomic potentials. So here, everyone that does simulations know about this trade-off that we can have between time scale or the system size that we can simulate. So this is approximate. And then on this axis, how much it costs or how applicable or general you can simulate. So you have coarse-grained models or classical force fields that you can do big stuff or simulate events that are very long, for long times, but they are not as accurate. So it's here on this axis. And for this type of nanoscale phenomena, we need to be accurate. So on the other hand, we have DFT or CNPEM methods. They are very much better. So you can simulate these things, but you can't reach time scales or size scales that we want to simulate. By using machine learned potentials, the idea is that you can get much more computational accuracy and efficiency while retaining almost as much of this original data set level of accuracy. And then once you have these things, then you can simulate different problems that this kind of force fields, they wouldn't work well. So these are in biology, chemistry, and materials. You'll see probably more works in materials, but things are starting to appear, especially in biology, which were not seen never before. And what is the idea here? So classically, what you would do when you want to simulate the dynamics of a system, as Mariana said before, you can do just a Newtonian dynamic. So you have F, force equals mass times acceleration, and then you map these things, the dynamics, onto a force field to get these forces that will drive your dynamics. How you can expand on your interatomic forces? You can either try to expand in known terms, so let's say single particle terms, in pairs of atoms, in triplets, and so on. So the idea is that you incorporate more data and you'll be more accurate as you incorporate more terms here. And then you can drive the dynamics here. But the idea with machine learned potentials is that what if we don't assume a specific analytical form and just gather it from the data? You see how, if you have a large enough data set, you can learn this representation given in the data that should be way more complex than these simple terms. And this is broadly the general idea of these methods. And then in machine learning, we have many different areas that we can apply these things. So if you want just the dynamics of the atoms, we do this, which is called atomistic machine learning. But you can incorporate electronic information. So we'll just comment on that on the end of the talk. But there are different approaches that you can also incorporate more interactions, and then you have ab initio machine learning and so on. So people are working on all of these different areas. Nowadays it's not different points, but there's a blur here, and everyone is trying to improve either in accuracy or in the reality or applicability that you can use these types of models. So what we need to simulate these things when we want to do machine learning interatomic potentials, the traditional route, as we saw before, you have the classical regression, where you have human-derived descriptors. You get your analytical form and so on. So we have examples like Lennard-Jones or ReaxFF, where you add different terms. You have a different class that doesn't force the functional form of these things, but you use still manual descriptors how to map your local environment of the atoms. So you decouple the two-body from three-body information and so on. And nowadays, most of the works that we see and use are based on graph neural networks, where each atom is a node in a graph representation, and then you have edges connecting these different graphs, and then both the functional form and the descriptors between them, they are gathered from the data. So you let the neural network find the best representation of local environments and also the functional form that connects the forces between them. And so you have a representation, some analytical technique to connect this, usually neural networks, and then you learn a potential energy surface information, which is high dimensional, but we represent here as a simple function. And the challenge is you need a good data set to map all of these informations between atoms, and you need to train one data set to one specific problem. So the idea now is being universal means you can train a single network on everything, covering the periodic table and also structural information, and then just a single interatomic potential can simulate anything from the whole periodic table and any structure. So this is what it means by being universal, both in chemical space and then structural space. And then, if we reach this, then we have this fingerprint, we have these models, and now we can simulate these kinds of problems, large-scale ones, probably on long-range scales, time scales also. So we can either do longer or bigger or faster or all at the same time. So this is the idea that we can use these interatomic potentials. So the question that we had in this work, it was quite practical, is can we use these things, the universal interatomic potentials, are they accurate enough? And what does accurate enough means? And then in the second point, if this fails, so we wouldn't have a second question if it worked, but if this fails, what is the most efficient route to improve on this pre-trained models? So comparing universal versus fine-tuning or from scratch. And this is from the community in artificial intelligence. From maybe some decades ago, we had machine learning, which we had learning algorithms, so different techniques. Over time, we reached it on the deep learning era, where now you not only learn the problem, the specific problem, but also the representations, so the features and the architectures. But nowadays, we are reaching the era in the different areas, so text, images, and so on, where you have foundation models that you try to learn a very general model, and then you can specify it on each specific problem later on. So now you learn functionalities from this foundation model. And this is one example. So you can have different modalities of data. They all merge into you learn a big model. And then once you have a task, then you can either fine-tune it or use zero-shot, meaning you don't need to retrain this model. So the idea is that if you merge everything here, you learn better than if you had one specific model for each problem. And in the area of machine learning potentials. The idea is that you can do many different things, not only optimization, you can do molecular dynamics of different systems, but now you can reach reaction simulations. I think we'll have talks about these things. So the applicability of these types of models are very much improved. And our motivation was this work about 5 or more years ago, where they did performance and cost assessment of what were the best at the time machine learning potentials. So all of these models, they assumed a very specific form, and most of them, they were not neural network potentials, except for this one. And at the time, this is the accuracy that you can get. So here on these plots, okay, so we had the errors on the energies, so milli-electron volts per atom. So these are the scales that we would reach on semiconducting systems or metallic systems and so on. So about 1 or a few 5 or so milli-electron volts per atom. And the errors on the forces of these force fields, they were around 2000 milli-electron volts per angstrom, about that, which is way better than the classical ones, but not accurate enough for many nanoscale systems. And then you can see here the cost and accuracy trade-off. So here's the computational cost on the number of molecular dynamic steps that you can do versus the error that, or the accuracy of each potential. So you want to go down and on the left as possible. So these were like just 5 years ago. And nowadays, none of these things are being used anymore. Like not a single one of them. So they're all old and no one uses anymore, or most people don't use it. And then sometime later, you have more works trying to improve on this front, especially on computational cost. If you want really cheap, comparable to classical force fields, and now you have potentials that are way more accurate than the classical ones and faster. So on this computational cost, this is solved. So what we did at the time, so we are talking 1.5 years ago, we had this benchmark that was published. It was called MatBench Discovery, that you try to train these universal models to predict novel combinations of materials, either in the compositional space or in the structural space. So there are different metrics assessing how good are these models, and we chose to investigate more in depth the topmost 3 models. So at the time there were these 3 ones. And as I said, just after it was published, it appeared 2 novel ones, and they were different because this came from Google and this came from Microsoft, and then it started their era of big companies working in this area. What? Training set size, so we were talking about hundreds of thousands, and then we reached the millions of training sets, and also the model parameters. So computational cost to train these models is scaled like quite something at this time. And what we did, we wanted to assess, so what is the first stage? So all of these training sets, they are on bulk materials. So they work quite well for bulk systems. And our first question was, what if you go beyond bulk? So our data set were coming from surfaces. So we had almost the whole periodic table. So we had about 1.5 thousand surfaces coming from a more than 100 bulk system covering 773 elements. And we wanted to see, okay, total energy is probably fine, energy is probably fine, but what about a simple next step, which should be surface energies? And then zero shot, you can see it's like you see below the diagonal, not good enough. We investigated if the errors were correlated with the surface chemistry of the systems, and mostly they are not. So it was bad in general. Also in the geometry, so the 3 indexes of the surfaces, they are mostly similar, so not specific errors. They were as good or as bad in all of the systems. And we can see a dimensionality reduction algorithm here. So there are no specific patterns, probably some metallic systems, but the errors are more or less spread out. So we compared, okay, universal interatomic potentials, they have probably not good enough. What if we fine-tune them, meaning we train on surface systems? So we see here, this is just a color image. I don't expect no one to see anything, but the errors diminish quite well. And they are usually better and more stable, robust than if you train specialized models. So this is one of the conclusions. When you have foundational models, they are usually better to fine-tuning. So this is nothing new in other areas, but in materials, at the time at least, it wasn't very much seen. And then we wanted to see, even after we fine-tune it, if you want to simulate the surface energy orders. So you want to see which surface is the least energetic one. And then they are almost at the limit where the errors cannot distinguish yet between these surface energies. So it's barely better when you want to use for some nanoscale systems. And this is, we tested many strategies and different models, and this is quite general, where you see a universal softening. So the models usually underpredict the energies, and there's specific reason for this, and so on. Relating performance of training these things. So this is just to show that when you fine-tune a model, you usually need a very low training time, so the scale of minutes, to reach, to improve on the original foundation model, and then you improve a lot the accuracies that you can get. This is just what to show. And this is one slide that I always need to update. So this was probably 3 weeks ago. This is the same MathBench discovery data set benchmark. And every 2 or 3 weeks or so, we have new models. And this is 2 axes. This is a combined performance, combining a structural and so on. So this means on the top, it's better, and on the left, it's better. So if you look around the models that we studied in our paper, they are probably around the worst ones. So nowadays, they serve to nothing anymore. And every 2 or 3 weeks or so, we have new models. And the topmost ones are now still at least in a competition between big companies and university groups, trying to improve either on the architectures or just on the computational size and efficiency of the training and so on. So just to comment, one of the most recent ones in May, it was released, is from Meta Research, which was Facebook. It's a family of universal models. You can see that the data sets are now reaching up to the billion scale systems now. So you combine here 100 million and so on. But this was the first time that we have a mixture of expert model for materials, meaning that these data sets, they are different ones coming from different DFT simulations with different parameters and so on. But when you use this mixture of experts, you can choose which accuracy level you want the outputs to be. So you can either predict at the PBE level, LDA level, and so on. So you have a single model that can output at the simulation parameter that you want. And just to come back to our problem, nowadays we are reassessing these most recent potentials for our original problem. So we have a data set, a large data set of this nanoscale neck and wire formation, and we are reassessing these things, and they look from 1 year ago to now, it's 1 order of magnitude almost improved compared to last year. So it's quite fast improvements. So I won't show the specific results. But once again, the zero shot and the fine-tuned strategy, it still improves by a lot. So fine-tuning usually in AI works well. So the question we had in the beginning is, do we have a ChatGPT, not in language, but for simulations? Yes, but something, or no, but you know, we have, but as always, you need to know what you're doing to use them. So how much out of domain is your application that you're trying to simulate? How much quantitative accurate you need to be for simulated systems? And universal systems, they, at the worst, they accelerate your workflow trying to simulate and understand systems. And if needed, you can use fine-tuning as a data-efficient way to accelerate the simulations. But in any case, in all of different areas, you not only need a large architecture, but you need a large, diverse, and informative data set to train these things. Even if you have a small data set, if it's informative, it's way better than just having a scale. And just to comment, to finish in about 1 or 2 minutes, what about electronic structure? So everything we talked about here is structural information, so classical dynamics. And this is 2019. I think this is probably one of the first works that is trying to use the same technology of neural networks to map from local coordinate environments to electronic structures. So this is in a local basis set, you get the Hamiltonian of the system. If you have the Hamiltonian, you can have the electronic structure. But at the time, it was not that accurate, and you can work with small molecules and so on. So these were the data sets that you have. And more recently, so 2022, we have now models that come from solid state and periodic systems. They were same idea. You have the Hamiltonian in a local basis, and the accuracy is getting better. You can now simulate twisted systems. To these systems get all the information that you can have once you have the Hamiltonian in a local basis set. You can train on non-twisted structures. We saw one example here before. But the most important thing is that the cost, computational cost to simulate these things, it's way down. So now you can access dozens or thousands of atoms in your systems. So this is about probably 1,100,000 atoms in the systems. The electronic structures are a few milli-electron volts, the eigenvalues from the DFT ones. And then 2023, it gets better. 2024, it gets better and more computationally efficient. You can simulate topological insulators, different systems, changing the structural from your data set. And this is probably my last slide. What we can do nowadays. So we got to 2024 and 2025. We can have these Hamiltonians with hybrid level of accuracy or more if you have that information. So now you can have these twisted systems with hybrid level of theory. So let's say twisted bilayer graphene. If you don't have correlations here, different types of, but so on, the hybrid level captures some of this. So you see the famous splitting here. You can also do million atom scale nowadays, simulations, with not that large computational infrastructure. You can have large memories, but still sub-million scales or million scale. So now you can get the electronic structure of really large things. So this is nanometer scale. You can get optical information that you can with the Hamiltonian and so on. And the final, connecting to what we are working with structural information, now we are reaching where we can have universal deep learning of the Hamiltonians, meaning universal, where you have a single model. Once you have the data sets, you can train the same ideas, but now output your DFT Hamiltonian. If it's not good enough, you can fine-tune this model with a modest data set, so hundreds maybe of electronic structure calculations. Most of us can do that quite quickly. And then you reach accuracies enough for most problems. So this is, as I said, in a national lab, we are mostly interested on these things as users, but maybe in the 1 or 2 years, this will be for everyone, and you can have these pre-trained models that will work, and you can trust on the results as you would with DFT. So with that, I'm done, and thank you. I hope for questions. Thank you.
Thank you, Gabriel. We have 2 minutes for questions, so it will be one quick question. You raised your hand first.
Thank you. I have a question about when you do this fine-tuning. How do you do this fine-tuning? Do you only use the weights and bias, or use the previous data plus your data to do the fine-tuning? How do you do this? Is only the data?
Good question. So this, we learn a lot from other areas from AI that are way ahead of us. So there are different ways to fine-tune models. You can be naive and just retrain everything, but you have the forgetting problem where you lose information that you had before. You can just train the last layers. It's not that good also, but you have more efficient strategies nowadays. You have replay where you incorporate previous information. You have ways of resampling the weights and so on. So we see what works in different areas and try to apply these things. But the naive way is usually not good enough. Yeah.
So I think we have time for one more question. I think you raised your hand. He raised before,
I
sorry.
have 3 here questions.
So my question is, first, like, great presentation, thank you. My question is more practical. Both Mariana and you mentioned how big tech companies also play a significant role in advancing research, mainly because of their power to gather large data sets. And I had never really heard of that in other areas of scientific research, so I would like to know, just like from practical experience, how that works, and how's the competition regarding the research done by universities and how that's developing. Thank you.
So quick answer. You probably heard of AlphaFold. So this was the Nobel Prize in Chemistry in the same year. So this is like also from DeepMind, Google. And any problem that is clear enough to understand and you can solve it by brute force, meaning applying more computational power or increasing the networks, the big companies will win. Where we have a competitive advantage or strategic one, when you need to incorporate either physics, biology, so the specialty in the area. So this is where the inductive biases, they improve a lot on the models. So if it's brute force, we obviously can't win, but maybe Mariana has a complementation.
Just to say that they have been making available all the data that they do. So they can produce data sets that we don't have the power, but they have been making publicly available. So I mean, they are producing.
Not all companies. Some like Meta Research, everything is open. Google, it depends on the area. They don't release. Yeah. Google is not famous for releasing these things and killing products. So, yeah, depends.
Okay, people. So we'll have the cocktail later, so you can discuss more with Gabriel. So to not get late with the program, let's thank Gabriel again.
Thank you. To not get late with drinking, we can talk outside. That's
drinking.
It. Okay. Thank you.
So now we'll have Christoph Brezina. He did his PhD at Charles University in Prague. His advisor was Harsalek? Yeah. Okay. And now he's a postdoc with Mariana at the MPSD Hamburg. So, Christoph, the floor is yours.
Okay. Thank you for the introduction. Thank you for the opportunity to be able to speak here. It's a great honor. In my research, I've been thus far, and I'm interested in the world of hydrogen-bonded liquids. And of course, these need very little motivation as to why we should study them, because everything happens essentially everything happens in a hydrogen-bonded environment, right? Almost all of biology, a lot of technology, many everyday, day-to-day activities that we know. So hydrogen-bonded liquids, mostly represented by liquid water, of course, are extremely important and of course, there's always need to study those. So I will talk about simulation. But I would like to open with an experiment. And I would like to open with an experiment that if you have studied chemistry in high school, you have probably done. And that is a reaction of alkali metals with water. And you probably know that this is a very dangerous experiment because it has an explosive kind of character to it. But my question to you is whether you have ever asked why does that happen? Why do alkali metals explode when you place them in water? And I would like to open with that. So when I did my master's in Prague, I had a British colleague called Phil Mason, and I think he can be characterized as a researcher who likes to do research that is fun. And he was always fascinated by alkali metals, and he had this brilliant idea to take a high-speed camera and make a video of this reaction with a great resolution and time, and this is the result. So this is a droplet of sodium-potassium alloy hitting the surface of water, and here it hits the water. And what you can see for a fraction of a millisecond is that when the explosion happens, you see this flash of blue color, and this blue color is a telltale sign of the presence of a species that we call a solvated electron. Sorry. There. So this is kind of the chemistry picture of what happens, right? So we know that if you put sodium into water, it releases hydrogen and creates sodium hydroxide, but it actually happens in 2 steps. In the first step, the sodium reacts with water and creates an electron, which very quickly becomes solvated and leaves over a sodium cation. And in the second step, this solvated electron very quickly again reacts with water, producing hydrogen and a hydroxide anion. And the reason for the explosion is that this dissolution of the sodium cation is much slower, which leads to positive supercharging of the metal droplet and a subsequent electronic instability and what we call a Coulombic explosion. So this is actually an electrostatic effect. So if you want to study these solvated electrons without your lab bench being kind of blown to pieces, it's very easy because you can just make one step back in the periodic table and change from water, which contains oxygen, to nitrogen, to liquid ammonia. And here you have these blue solutions that are completely stable, and you can work with them at cryogenic conditions. And these have very many very interesting physics going on. One of them is that if you actually increase the concentration of the alkali metal that you put in them, these electrons that you have in the solution start interacting together, and they eventually fuse to a metallic structure, and you have this electrolyte to metal transition accompanied by this vibrant color change. And we have been able to gain a lot of insight into these systems in my previous work from molecular simulations. And what we are looking at, this is an ab initio molecular dynamic simulation of a solvated electron in liquid ammonia. You are looking at the green thing is the density of this excess electron. You can see how it forms this bubble of charge that floats around in the solution. That is liquid ammonia. So this is hybrid DFT that we did. And so I would like to open the actual theory part with kind of doing a little hierarchy of simulations. We have heard a lot about that, but I'll just do a quick summary. Thanks to both of the speakers for making this easy for me. So in this talk, we will stay within the framework of the Born-Oppenheimer approximation. My colleague George Trennan, sitting somewhere there, I'm sure he will tell us on Wednesday a lot about what we go beyond it. But here we will stay within the Born-Oppenheimer framework. What is this? So we have in the beginning our full quantum dynamics, our electrons, our nuclei interacting together and evolving in time. This is of course nice, but for realistic systems, that is sadly intractable to use it for the simulation. So we often invoke the Born-Oppenheimer approximation, which splits the problem into a nuclear dynamic problem where the nuclei move on this effective Born-Oppenheimer potential energy surface that we obtain from the solution of the electronic Schrödinger equation. And as a further simplification that people often do, they would invoke the classical approximation for the nuclei, and then, as Mariana mentioned in great detail, we can solve classical equations of motion where the forces are defined as the gradient of this Born-Oppenheimer potential energy surface. And if we want to describe our nuclei quantum, we typically, using quantum mechanics, we typically do not rely on the wave function formalism as shown here, but we invoke the path integral methodology that allows us to use classical methods on an extended phase space. So let's do a little diagram here. So on one axis, we can have the nuclear description that I said we can have either classical or quantum. And on the orthogonal axis, we would have the electronic description. Of course, we are not going to talk about classical electrons. That doesn't make sense. They're too small. But we can have electrons described ab initio, or from first principles. That means by explicitly solving something like this, or we can have an empirical potential where we assume a known functional form for this Born-Oppenheimer potential NG surface. And so the computationally most easy and least accurate would be known as force field molecular dynamics, often used in the world of biophysics. Then we can have force field combined with PIMD, quite rare but exists. Classical AIMD, which is what I showed on the previous slide. So classical nuclei on a ab initio potential NG surface. And finally, we have path integral methods with ab initio potential NG surfaces, which would be here. And of course, this is how the accuracy grows, but also how the computational cost grows. And sadly, if we want to talk about hydrogen bonded systems, they end up here, because for these we need the ab initio structure to describe well the intricacies of the electronic effects in hydrogen bonds. And of course, we are dealing with the lightest nucleus, so the quantum effects are the most pronounced, and we need quantum nuclei for this. So that's quite sad, because ab initio molecular dynamics with path integrals especially quickly become unmanageable due to high computational demands. And this is a place where neural network or machine learning and neural networks come into. So I'm going to talk about neural network potentials in this work. So what are these? So as I said, we have our ab initio potential energy surface, and we obtain the forces to drive our dynamics as a gradient of this potential energy surface, which is very expensive. So what we do is that we assume not a force field form, but a neural network. So we express this potential energy surface as a neural network, which is just a function of our nuclear positions and parameters of the neural network, which we will call theta. And if you have done any machine learning, you know that these are the weights and biases of the model that we and we find these by defining what we know as a loss function, that is a function of these on this parameter space and of a training set D that we call D here, and we perform a minimization of this loss function to obtain an optimal set of parameters that gives us a good fit in this energy. So as an example, we have heard in the previous talk that there are many ways how to do machine learning potentials and neural network potentials specifically. I'm going to talk about a relatively old but a relatively simple example. And so this is the Baylor-Parnello neural network. So we start by feeding in the atomic positions, mapping them onto a set of descriptors that we call atom-centered symmetry functions, and feeding these into what we call atomic neural networks. And these atomic neural networks, they give us these atomic energies that we then sum to obtain this final energy. And these descriptors, they are necessary to ensure the correct symmetry properties of the potential energy surface with respect to rotations, translations, and permutations of atoms of the same kind. So these come in two forms. These would be the which we call radial, that depend on the distance between two atoms. And then we have angular ones that depend, of course, on the angle between two atoms, and these represent 3-body terms and 2-body terms. So now the question I want to answer mainly in this talk is how we obtain the data set for training these potentials, because this is a crucial part on the way to obtaining an accurate and good potential, and it's not an easy one to answer. So you could start by imagining we have some candidate pool, which we call it's a bunch of structures that we select from, and you can say, okay, fine, so I'll take the easy way and I will just select random structures. Is this good? Well, it's simple for sure, but it doesn't have to be the best way to do it, because this is not a let's say data-aware way how to select these structures, and we can miss information from the potential energy surface, or we can create some holes in kind of coverage of the potential energy surface like this, and this is what shouldn't happen, because it will lead to inaccuracies in the resulting model. So a better way to look at this is by active learning, which is what I'm going to introduce now. So let us imagine let us imagine that our model estimates also the uncertainty of its prediction. So this neural network will give us the energy and also some measure sigma that tells us how uncertain the model is about what it predicted. And this is typically not a case in neural network, because a trained neural network has a fixed set of parameters, and the output is of course deterministic, right? We often get the same output if we let the neural network predict on a given input, but we don't have the measure of sigma. Let's just imagine now we have it, and I'll talk about how we get it a bit later. So if we have this, then the model can select the most informative training data and prevent this training set dilution. By that I mean that it only picks data that contain certain information, not let's say not multiple times, and we prevent redundancies in the training set. So here is a schema as to how that might work. So we start with a candidate set that we call here C, and with this measure sigma, we iteratively at each iteration we select a number of highest disagreements, highest uncertainty structures, and we add them to this training set that we have called D, and that is a subset of C, and we train a neural network on this. So we obtain a model, and then we let the model predict on the candidate set again, and we do this iteratively until we are happy. This is one way to look at it, but we can also introduce a sort of a fork here, and we use this model to actually drive a molecular dynamics simulation that we call an exploration or exploratory molecular dynamics simulation, that the role of which is to as the name suggests, to explore the potential energy surface and give us new information, discover new landscapes that we have previously not visited maybe, and that we need to represent in our training set in order to gain accuracy in those regions. And then of course we put these structures that we have collected back to the candidate set, and we can stay again on the red loop and then do this kind of in a iterative way. So now, how do we obtain this uncertainty measure for neural networks? So one way to do this is not to have one model, but to have a set of them, an ensemble that we call a committee, and we train these by initializing the training procedure differently for each one, so they end up in let's say different parts of the parameter space. They are different models, but they take the same output, and they are trained for the same purpose. So what do we get out of the model set such as this? So we of course get from each individual model we get a prediction, but we also get an average of these, which will be the potential energy surface that we will use to represent our reference potential energy surface. And crucially, we also get the standard deviation of this model, which is our measure sigma. We call this committee disagreement for the purpose of committee models. So here's an example as to how this might work in practice. So we start with an ab initio simulation. That would be the black line. And we initiate the procedure by selecting a few random points from this. We get a model, and this model, we get a committee model, and this committee model gives us, as I said, several individual predictions, but it also gives us an average prediction and a measure of uncertainty, right? And we continue by looking at the uncertainty for each point in this candidate set, picking those that have the highest measure, highest value of disagreement, and adding them to the training set. Iteratively, we do this many times until we reduce this disagreement to bounds that we are happy with. So 2 notes. So this iterative selection that we know as query by committee selects these highest disagreement structures and targets, of course, outliers that the model is the most uncertain about predicting. And this leads to a robust and uniform and compact, I would also add, training sets. Just a note, this committee disagreement, this measure sigma, is not the same as the quantity that we known as the generalization error, that is the actual error of the model, but they are known to correlate, so we have to execute a little bit of care if we want to interpret this as the actual error of prediction, but well, there are ways to do that as well. As an example, I would like to talk about active learning water across the phase diagram. So what we started with in our work is a simulation of liquid water at 300 Kelvin simulated by classical ab initio molecular dynamics using hyper-DFT, right? So this was a short simulation that we see the procedure with, and we want to describe water in all many of its forms, let's say. So we'll start by doing the query by committee. If you remember the diagram from the previous slide, we will stay on the red loop, and we get a model for this. This is very simple, and with this model, we can, of course, now the model is trained for this, so we can have long simulations of liquid water. But what we can also do, where the real power of this method lies, is that we can explore new conditions. So we can explore liquid at different temperatures. We can, for example, explore also ice phases with this model. We can explore the water-air interface, and we can, of course, start quantizing our nuclei with path integrals. So how this works? Well, we perform the simulation with this model, and we use this as a new set of candidate structures that we iteratively then add to our training set via query by committee to improve the model in these regions of the phase space, right? And we can continue with that. We can extend to water at different ensembles. So here the isobaric ensemble to different phases of ice, etc. So and the nice thing here is that query by committee-based active learning is very efficient in this. So our final water model was only trained on 800 geometries, has small generalization errors, and of course, no ab initio molecular dynamics was ever performed at any stage of this iterative improvement. The only molecular dynamics was the one that was used to seed this whole thing. Okay, so in chemistry, liquid water, you can understand the liquid water as a sort of maybe Drosophila, or like a basic system that we always aim to describe first. But chemists are often interested in what happens when we put stuff in the water, right? And what we did in one study is that we put a benzene molecule in the water. You might be asking why that is interesting. That is quite interesting, for example, because if you imagine we would have an oil spill on the sea, the oil contains quite a lot of benzene, and benzene is surprisingly soluble in water for an organic substance. And when it dissolves in the water, it has a much far-reaching impact on aquatic life. And of course, then if we want to study these situations, we need to understand what the solvation of benzene looks like, right? So this is what we did here, what we can do with these machine learning potentials. And when we talk about solvation structure, we often talk about these probability distributions, right? So this is the probability density of finding an oxygen atom in the proximity of the benzene molecule. We can see that we have patterns of two types. We have these stripes, and these correspond to the expected, what we would expect to be the hydrophobic solvation that is common for hydrocarbon species in water. But we also have these peaks here, and these are something different. These are something much more structured, much stronger, and this something is called a pi hydrogen bond, right? So this is when the water molecule comes and actually interacts with its hydrogen with the negatively charged pi electron cloud of the benzene molecule, and forms an interaction like this. And well, you might be asking, is this real? Are there experiments that can see this? And the answer is yes. In 2011, there was a Raman measurement of exactly these solutions of benzene in water, and they find, so this is a Raman spectrum. We have the vibrational frequency and the Raman intensity here, and this would be the dashed line would be the OH stretching peak of water. And they find, if they perform a very, very fancy analysis, which is essentially a kind of well-informed subtraction of neat water, they find there's this little peak left over that is at the high frequency end of the stretching peak and they claim to correspond to these pi hydrogen bonds, right? And so we were like, well, we are in the positions when we have these simulations, or we are in the position when we have these simulations that we can gain insight into this from simulations. So this is the simulated vibrational spectrum here. We're looking at a quantity called the vibrational density of states. And so this is, let me take you through it. So the gray one would be the full spectrum. So this is the OH stretching peak of water. And if you look at the molecules that are only in a pi hydrogen bond, momentarily in a pi hydrogen bond, we really find that these are located at the high frequency end of the water stretching peak. And if you look at our molecule, at other molecules in the first solvent shell of this that are not in a pi-hydrogen bond, we see that these are unaffected. And in order to kind of understand this, we have to look at a very, very simple thing, and that is a potential energy diagram as a function of an OH bond distance. So what we are actually doing, we are taking the water molecule and we are stretching the OH bond, and we are looking what happens with the potential energy here, right? And so for a single water molecule, that's the black line. It has a minimum, and it grows on both sides of the minimum. What is interesting is that if we take another water molecule and we form a hydrogen bond and perform the same exercise, we see that the curve is a little bit more open, right? And a more open curve leads to a narrower spacing of vibrational levels, and of course a decreased frequency. So a vibrational frequency. So what is the takeaway message from this is that in liquid water, which has these hydrogen bonds, the OH stretching frequency would be shifted to lower frequencies in comparison to the gas phase. And in a pi hydrogen bond, this is a much weaker hydrogen bond, then this is no longer the case, and the OH stretching frequency is kind of a blue shifted again with respect to bulk water, right? And to kind of drive this point home, we can switch the water for liquid ammonia and do the same exercise, the same simulation. And ammonia, the point about ammonia is that it also has hydrogen bonds, but these are much, much weaker than in water. And if we do this, then we find that indeed in ammonia, all of these are the same. There's no shift because molecules in liquid ammonia and gas ammonia are essentially the same. Okay. So I just wanted to mention here that vibrational spectroscopy, especially combining accurate simulations with advanced experiments, can serve as a detailed probe and a very flexible probe into solvation structure. Okay, so now I would like to, for the last part of the talk, I would like to switch gears a little bit, and I would like to talk about machine learning, building machine learning models for chemical reactions. So thus far, I have talked about systems that have no reactions, solutions, liquid water, and stuff like that. So that's quite nice, because when we have no reaction, we perform some initial dynamics. The system samples our thermally available potential energy surface. We gather those structures and we train our potentials of them. We can do this in a nice way with active learning, as I have introduced before. But the problem with reactions is that when we have a potential energy surface that corresponds to a reactive transition, so we have a barrier that is much larger than the thermal energy, and we initiate the system here, it samples only this minimum, but it will never, it will never go over this barrier, right, on its own, because the barrier is just too large and the probability of happening so is vanishingly small. And so what this means for machine learning potentials, if we want to describe these reactions, we need all these structures. We need the structures from here, but also from here and from here for the model to be descriptive across all the reaction, right? But the representation of these transition structures requires extensive ab initio sampling, right? So that would mean we either need to do a simulation that would be extremely long, or we need to resort to what we know as enhanced sampling methods, which is a much better idea than doing simulations that are extremely long, but it's still computationally extremely expensive and quickly becomes prohibitive. So I would like to talk about a piece of methodology that we have developed for this purpose that we have named transition tube sampling, and that gets us these transition structures efficiently, right? So I would start with a 2D representation of this, and then I will introduce some examples. So here we have a sample 2D potential energy surface, which has two minima and maximum and transition state. This is maybe a model of a reaction, right? So in real life, we don't have a model like this, but this would be our DFT potential energy surface. And in this method, there are two, let's say, preliminary steps, and then we generate the structures. So first, we need to find a path that describes the reaction. This is typically what we know as the minimum energy path, and this is what we typically do well, always essentially, because we can systematically find minimum energy paths for any reaction. But if you happen to have the chemical intuition and guess this is just good for us, because then it's cheaper. But we can optimize the minimum energy path in every case. And what we do is that we pick a few important points here, and we calculate normal modes, calculate the harmonic expansion in these modes, and well, this gives us frequencies and normal modes at each of these points, right? And now we come, yes, okay. And now this brings us to the interesting part. So we want to get these structures that we will use as a base for our machine learning models. We erect a uniform distribution of points along this path, and then we use these normal modes to distort these structures. So we take these points and we add a distortion that is composed of these normal modes. So this is just the mass matrix, the normal coordinate, and the normal mode that we project in the direction perpendicular. It can look something like this. And we draw this from the harmonic Boltzmann distribution. So we actually create thermal distortions in the perpendicular direction. And then we take all these red points and we dump them into our machine learning, active learning procedure and select the best structures. Okay, so I would like to show here, just to finish my talk, 2 examples of this. The first one will be gas phase. So this molecule is called melanaldehyde, and it's a model for a simple reaction. So this here we have a proton and 2 oxygens, and the reaction is just sharing this proton between these 2 oxygens. So this is represented on a diagram like this. So here we have our what we call a proton sharing coordinate defined here. They just describe the movement of the proton between these 2 oxygens, and on this axis we have the oxygen-oxygen distance, because as the proton is exchanged, they become a little bit closer together, and this leads to this V distribution. So as we had on the example before, here we have our MEP. This is the path that starts our transition tube sampling, and this blue distribution is the points that we have generated. And what is important to mention here is that this this is based on the harmonic approximation, right? So it contains harmonic sampling, but due to the active learning procedure, we know the anharmonic energies. And this, of course, kind of points us to the limitation, because if we make the model out of this and we run the exploratory molecular dynamics simulation, we can see that wherever we have covered the potential energy surface with points, we are doing quite good. So this is just samples from the simulation covered by the colored by the force disagreement, but we can see that we have these tails of this distribution that are not represented very well, because, well, what happens in real life is that we have the harmonic wall that we have imposed by the transition tube sampling, but we in real life this is essentially anharmonic. This is very common in molecules, that they behave anharmonically. And of course we have this high disagreement here, because the system just samples further but doesn't know what the prediction should be, right? And so this brings us to the limitation that this method is limited by its inherent reliance on the harmonic approximation. The question is whether we can do something about that, and the answer is right there. So this is the plot as we had on the previous slide, and I have described query by committee active learning that is based on the highest disagreement structure. So if we take these structures as a new candidate set and we dump them into the procedure, this will aggressively target these high disagreement tails, and well, in the next iteration, the model is already improved in this problematic region and has sampled a little bit farther. There are some new structures that are again harder for the model to predict. We do it again, and then we are, of course, done. This is a model that is descripted over all the anharmonic thermally available potential energy surface. So active learning on top of TTS can tackle anharmonic landscapes. And as the last part, I would like to talk about a surface physics problems where we have water on a surface, and we want to understand what happens when we split this bond, when we have water splitting. So we start with this monomer, and I will now explain how we obtain the structures using transition sampling, and I will finish off with some results. So this is the MEP, how we are splitting this water molecule. We can see that This is primarily described by the split OH distance and presents a barrier of approximately an electron volt. And if we do the transition tube sampling with this MEP, minimum energy path, what is actually happening is that we are making this MEP a little bit fuzzy with these thermal perpendicular distortions to account for structures that we can meet in a molecular dynamic simulations, and we gather them and build our models on these. But in real life, of course, we are the monomer is just an approximation, and we are interested in something more like this. So when we have a metal-liquid interface, and we want to see what happens when we split this water molecule that I have highlighted now in green. And of course, here we run into a little complication, because we have the solvent dynamics that is well characterized by a multi-minimum thermally surmountable potential energy surface. So we can sample this by molecular dynamics, but this is of course very anharmonic and completely inappropriate for transition tube sampling to be used for that purpose. So we have, and on the other hand, we have the reaction that is well described and efficiently described by transition tube sampling, but not by molecular dynamics. So we have to take the best of these both worlds, and we start by performing a molecular dynamic simulation to sample this liquid metal interface. This allows us to get structures of the solvent moving around, and then we take some certain starting points, and we pull these transition tube samplings of the reaction, and we just perform what we did in the previous slide. We collect these structures, and we, as a whole, we okay. Time's over. Okay, here we go. I'm finishing just in a second. We again introduce these structures into the active learning protocol, and we can get a model that is very accurate. Here I just wanted to show in brief how we compare how much computational time we are saving by this, right? And here's a study that does something like this, using an ab initio sampling on these of these reactions for a similar system, and this here we are essentially in the ballpark of a million force evaluations. With transition tube sampling, we are actually essentially decreasing this by several orders of magnitude. So this is really good for these extended, expensive systems. I think I'll finish here. I'll just mention a few conclusions. So NNP accelerated AMD simulations are a powerful tool. Active learning makes the preparation of NNP data aware and efficient, and we can do reactions well even in the condensed phase with transition tube sampling. If you want a hands-on experience on this, please come to our, if you are still here around on Thursday, please come to our tutorial on active learning. And I would like to thank Mariana, her group, and then everyone involved in my research. I'm very grateful, and thank you for your attention.
Thank you. So we have time for 2 questions. Let me go to Christian.
Thanks for the beautiful talk. In the very beginning, you mentioned that you're using the highest uncertainty to basically pick new training samples in this active learning scheme. In my experience, you then choose high energy structures, because just by higher energy has higher error or higher relative error. So you then retrain basically on the high energy manifold that encompasses your phase space. But usually, especially if you're after barriers or rare or not so rare events, you want to target, the inner of the phase space that is thermodynamically easily accessible. Do you tailor your kind of active learning strategy to point at this?
To point to high energy structures, you mean?
Or medium energy structures. The high energy structures are thermodynamically usually not.
So the problem is with this, is that with exploratory simulations, we typically do not know what these energies are because we obtain a candidate set, right? We do a simulation and we don't have the energy labels for this, so we have to label them on the fly. And we can do this with active learning. So we label the points on the fly, we get these energies. And the goal of getting the training set right is to cover the potential energy surface kind of as a whole uniformly as possible, because we don't really need very many structures in one part and a few structures in another part. We need a uniform coverage, so the neural network, or the machine learning potential in general, doesn't have to be a neural network, has knowledge about that specific part of the potential energy surface. So what we are trying to do is actually scatter these points, not according to thermodynamics, but according to the need of the model. And this is where active learning is really good, because it can tell us what these structures that are missing in the existing candidate set, and where we have to go, and where we have to add structures. This is what it tells us.
Thanks.
So we have time for a quick one. You?
First of all, thanks for the talk. And I would just like you to clarify a bit what you said about the difference of the model error in the query by committee that you do and the
first disagreement, the energy disagreement.
Yeah.
I would invite you to the tutorial again, because this is something we will discuss in more detail in there, but just in brief to set the stage for that. So you can imagine when we predict with a neural network, we have this regime that is called interpolation and extrapolation, right? So when we are on a part of the potential energy surface that is well covered by data, we just need to interpolate the energy between the data. This is where the models are really good. Where they are typically very bad is the extrapolation regime, right? And so, because they don't know they don't have the information of what happens there. And what happens with the committee model is that the predictions of the individual members, they would just drift apart, right? So this is the reason why the variance of this, if you take the variance of these predictions, that grows. And of course, then the difference between the actual reference energy obtained from DFT and this average of the committee is something that also they drift apart more, right? But they're not the same thing, right? So the variance and the actual difference from the reference is two different things, but they can be shown to correlate, and then we will do that in the tutorial.
So thank you all. The session is over. Let's thank Christoph again. So now you're invited to the cocktail outside. Thank you all.